हम लोग स्टार्ट करने वाले टाइम सीरीज। टाइम सीरीज का कुछ कुछ एस्पेक्ट, जो मतलब टाइम सीरीज क्या है, कहाँ यूज होता है, डेटा स्ट्रक्चर कैसा दिखता है, ठीक है, ये सब में हम लोग इंटरेस्टेड उतना नहीं है क्योंकि सबको ये पता ही है क्या चीज है, ठीक है। तो बेसिकली हम लोग स्टार्ट करेंगे कि एक टाइम सीरीज डेटा है, उसको हम कैसे डिट्रेन करेंगे। डिट्रेन मतलब कि उसके पहले ट्रेन क्या होता है वो देखेंगे, डिट्रेन कैसे करेंगे देखेंगे, उसके बाद धीरे धीरे करके स्टेशनरी कैसा होता है, नॉन स्टेशनरी, ये सब में चलेंगे। ओके, सो फर्स्ट ऑफ ऑल एक टाइम सीरीज का जो टाइम सीरीज एनालिसिस का जो अप्रोचेस है, सो उसमें से मोस्ट इंपॉर्टेंट अप्रोच इज द ट्रेडिशनल अप्रोच। That is mainly used by the most of the practitioners. So here in this approach, we basically what we do actually, we decompose the time series, or we basically decompose the variation of the time series, decompose the variation into some four major components. So what are the four major components? One is the secular trend, जो हम लोग बोलते हैं कि रेगुलर ट्रेंड भी बोलते हैं कभी कभी, ठीक, that is denoted suppose as TT, and one is suppose seasonal trend, that is ST, one is cyclical trend, that is denoted as CT, and one is the random trend. So random का मतलब क्या है, irregular trend इसको हम बोलते हैं। Suppose it is our irregular T. Okay. So here, this secular trend, cyclical trend, and seasonal trend are the systematic part of the time series data, because we know that there is a permanent cause or prediction, जो भी होता है हम लोग use कर सकते हैं। But this irregular जो components है, that is called the noise. Or you can मतलब suppose we are handling a signal data, signal processing data, where we have YT is our time series data. In there IT, that is our noise. Okay. So first of all, what is secular trend? It is the long-term movement of the time series data, and seasonal trend is the suppose it is the variation which is caused by a regular periodic. Okay. इसमें हो सकता है कि द पीरियड कैन बी ऑफ 1 year और 5 year और 10 year, कुछ भी हो सकता है। एंड वन इज द साइक्लिकल कंपोनेंट, इट इज साइक्लिक वेरिएशन, मे बी अप एंड डाउन मूवमेंट जो भी होता है उसको बोलते हैं हम लोग। और रैंडम वेरिएशन जो हम लोगों का दिखता है, दैट इज कॉज्ड बाय बेसिकली द प्योर रैंडम। ओके, सो सपोज वी हैव अ मॉडल that is YT equals to T plus S plus C plus I. So this is called additive decomposition. So basically हम लोग बोलते कि इसको मतलब फॉर एग्जाम्पल मान लो कि if suppose every month of September a car company sells thousands units of cars, okay, and that is more than the month of October. So that is a component for the additive seasonality. Okay, and suppose we say that the car company sells 30% more cars than October, then it is called the multiplicative in nature. Okay, so additive seasonality, this is called the additive decomposition, and we are going to use it when we have the absolute amount, and we are going to use the multiplicative one, that is called the multiplicative. So it is going to be used when we have a constant factor. Okay, so these are the components. मतलब इसको हम लोग डिकम्पोज करने का बहुत सारा तरीका होता है, ये सब हम लोग कवर कर सकते हैं, ठीक है। So just skip that part and let's move on to stationary process. So basically there is a theorem. Let me write it. Okay. So suppose we have YT, that is the time series, and where expectation of YT that is equals to 0. Okay. So okay, before going to stationarity, first let me give you some descriptive measures why we are considering expectation of YT is 0. Okay. First of all, this expectation of YT, that is called the mean function. Okay, and we can also have expectation of YT minus mu t squared, that is called the variance function. Okay, variance function. So उसको हम लोग बोल सकते हैं sigma square t, and mean function can be denoted as mu t. Okay, so basically these are the descriptive measures, and also we can also write auto covariance function. Yes, I think you guys know that. So let me just go through it. Auto covariance function, that is called ACVF, that is denoted as gamma kt, that is suppose covariance of YT and YT plus k. Okay, so here we can write it like in terms of expectation of YT minus mu t and YT plus k minus mu t plus k. So this is called the autocovariance function. Okay, and we can also write gamma naught t, that means this is the variance term sigma square t. So using this, we can also have the autocorrelation function. Autocorrelation function, that is also called as ACF. So here K in ACVF, K is called the lag. Lag means the difference in the time points. T plus 1, T plus 2, these are the different time points. So autocorrelation function, it is denoted as rho kt, autocorrelation function of suppose lag k. Okay, so that is equals to gamma kt, that is the autocovariance divided by the variance term. So what is the variance? Sigma YT square into sigma t plus k square of y. Okay, so 1 by 2. So that is the autocorrelation function. So obviously when we have rho not t, that should be 1. Okay, because both are same, right? So there should be no one variance. So if we express this autocorrelation function in terms of in a matrix format where we have k cross k matrix and all the correlations are in there, then in the diagonal we have 1, and in the off diagonal we have some other values. Okay, so suppose we have mu t, that is equals to mu for all t. Mu t is constant. जितना भी टाइम पीरियड है, हर एक टाइम पीरियड के लिए mu t is constant, and sigma square t is also sigma square for all t. Okay, and gamma kt, that is equals to gamma k. So here basically that gamma t only depends on the lag. The covariance function जो होता है autocovariance function, that is only dependent on the lag, not only the time. Then our ACF will be rho k, that is equals to gamma k by gamma naught. Okay, so this autocorrelation function have some properties like the autocorrelation function है gamma k less than equals to 1, non-uniqueness. Okay, क्योंकि मतलब कि एक स्टेशनरी प्रोसेस है, so एक स्टेशनरी प्रोसेस में क्या होगा कि रो के इक्वल्स टू माइनस रो के होना चाहिए. ओके, एंड क्या होगा कि इस स्टेशनरी प्रोसेस मतलब उसमें क्या होगा, when we have compute the mean, variance, autocorrelation function, it is always possible to obtain several non-normal processes with same autocorrelation function. So we should have the non-uniqueness property in autocorrelation function. Okay. Next one is important. There is an important theorem. So suppose the ACF of a purely random process. That means we do not have any train, okay? Or you can write it like GWN. That is called Gaussian white noise. That is given by, it's like rho k equals to 1 if k equals to 0 and 0 if k not equals to 0. Okay, so all the covariance is 0. Okay, so मतलब जब कोई covariance नहीं रहेगा, then we can say that the autocorrelation function is the only, or you can say only have the random component. Okay, other components are not in the time series data. Okay, so there is also a result from here. So suppose yt is our time series and expectation of yt हम लोग इधर से start करने वाले थे, that is mu. Then the autocorrelation rho k is the value of a which minimizes the function expectation of yt minus mu minus a into yt minus k minus mu whole square. So basically it's not in there, not in the outside. Okay. So basically एक autocorrelation function का जो value होता है that is minimized using by the function of this. Okay. And we can also calculate the sample autocorrelation function. You can go through the formulas. Sample autocorrelation and जो भी है ACF आएगा, ACVF आएगा, ठीक है, उसका तुम लोग फॉर्मुलेशन एक बार देख सकते हो. वही है कि you can denote it as R1, that is equals to n into summation yt minus y bar, that is a sample mean, yt plus 1 minus y bar, okay, divided by where t equals to 1 to n minus 1 and n minus 1 into sum over t from 1 to n yt minus y bar whole square. That is a sample R1. Okay, and we can also find the other autocorrelation function. ये सब जो भी है हम लोग निकाल सकते हैं. Okay, leave that part. What we require is the terminology correlogram. So correlogram, we know that. What is the correlogram? Basically the diagram in where we represent all the correlations in our data set, right? So similarly, एक हम लोग graph draw करते हैं. In that graph, we represent all the correlations. So what is that? Basically, it is called like suppose RK. Okay, and the graph of RK against all the lags, मतलब एक कोवेरिएंट फंक्शन है जिसमें lag 1 to up to k, and similarly here lag 1 to up to k is represented in there. So we are going to use it for identification of the covariances. Okay, so ये बस ये याद रखना. But there is one more tool that is called the partial autocorrelation function. That is called PACF. So basically, this our PACF. So the PACF of order k, we denote it as suppose alpha k. That is the partial correlation coefficient. Partial correlation coefficient between yt and yt minus k. Okay, so that is called the partial autocorrelation function. So कोई मान लो alpha k is the autocorrelation between yt and yt minus k. That means we are conditioning that the correlation between yt and yt minus k, removing all the dependencies on yt minus 1, yt minus, sorry, जो भी जितना भी बाकी है up to yt minus k plus 1. ओके, जितना भी टाइम पॉइंट्स है उसके ऊपर जो लीनियर डिपेंडेंसी उसको रिमूव करके हम लोग पार्शियल कोरिलेशन निकालते थे. सो दैट इज डन इन हियर. ओके okay, next is that we can also have the least square residual of the linear regression. मतलब जो हम लोग करते थे कि partial correlation, partial regression, in that case we can also find et k minus 1, that is the least square residual of linear regression in between yt and yt minus 1 up to yt minus k plus 1. So if you try to find that, मतलब कि इसको अगर expand करोगे, then we can have the expression of the PSEF. Okay, so basically the expression of the PSEF is denoted as, suppose we write it as zk minus 1, that is equals to yt minus 1 up to yt minus k plus 1 transpose. Then we can have expectation of yt zk minus 1, that is equals to, it is a rho to the power k minus 1, and expectation of yt minus k zk minus 1, that is rho k minus 1, rho k minus 1 star, suppose. Okay, so using this we can find, इसको use करके we can find alpha, that is the going to get using the least square residual, जो भी हम लोग पहले बोला उसको use करके we will get p to the power k minus 1 inverse rho k minus 1. So both are matrix, p and rho are matrix in form of those yt's and the rho, जितना भी रो है उसका. ठीक है, तो ये तुम लोग एक बार चेक कर सकते हो. And we can have the autocorrelation function, that is by rho k minus 1 transpose pk minus 1 inverse and rho k minus 1 star divided by 1 minus the same thing, rho k minus 1 inverse, sorry, transpose pk minus 1 inverse and rho k minus 1 star. So that is how we can calculate the partial autocorrelation function. So you can go through this कि कितना properties है ना है. Okay, fine. And the next thing we are going to talk about how we can obtain the PSEF. Okay, so there is a theorem. So suppose we have a time series yt and expectation of yt, that is equals to 0. Okay, so then we can find the autocorrelation function, sorry, partial autocorrelation function of order k by using the last coefficient akk that minimizes the difference, sum of squares of differences. That means suppose we eta equals to expectation of yt minus summation of aki yt minus I, sum over होगा I equals to 1 to k whole square. Okay, so this is how we can calculate the akk, in which is the our partial autocorrelation term, and that is called the Darwin-Levinson algorithm. So that is can be obtained by Darwin-Levinson algorithm. Okay, so ये सब थोड़ा सा याद रखना चाहिए. हाँ अनिमेश बताओ.
सर क्या ये आप रिपीट थोड़ा कर सकते हैं? डार्विन लिविसन मतलब क्यों यूज करते हैं ये वाला लाइन?
बेसिकली हम लोग क्या कर रहे हैं कि जो ऑटो कोरिलेशन मतलब पार्शियल ऑटो कोरिलेशन फंक्शन जो है दैट इज आल्सो कॉल्ड एज PACVF, सपोज को डिनोट करते हैं ऐसे करके. So that is actually getting by the minimization of this function. Okay. So ये क्या है कि sum of squares of जो differences है random term जो है random component उसको हम लोग उसका variance को minimize कर रहे हैं. Okay. But in Darwin level इसको ये बहुत लंबा चौड़ा एल्गोरिथम है, मतलब बहुत लंबा है ये. बट इन डार्विन लेविसन एल्गोरिथम में क्या होता है कि ये जो पी के है इस मैट्रिक्स को हम लोग रिकर्सिवली इसका मिनिमाइज करते हैं, मतलब यूजिंग रिकर्सिव प्रोसेस. ओके, सो दिस इज एन एल्गोरिथम टू ऑब्टेन द PACF बेसिकली. तो इसको तुम लोग अगर देखोगे ना एनिमेस कि थोड़ा बहुत पढ़ोगे तो डार्विन लिविसन का एक लंबा चौड़ा थ्योरी है. ओके, तो उसमें क्या होता है कि जो अल्फा के आता है ना, अल्फा के उसका वैल्यू आता है वही जो मैंने लास्ट पेज में लिखा था ना, दैट थिंग विल कम इफ यू यूज द डार्विन लिविसन एल्गोरिथम. Okay.
Okay, sir.
Okay, fine. Next thing, we have to understand why we are talking about the random component, right? So basically, we can have a purely random process. That is also called as random shocks. Okay. So suppose we have a discrete process. I hope कि तुम लोग discrete process पता है, stochastic में किए हो. So mu t belongs to t, that is called a purely random process if the random variables ut t that are a sequence of some IID random variables. Okay, so maybe मतलब इसका क्या properties है? The properties are like it has constant mean, constant variance. Okay, gamma k that is equals to 0 for all k. Time series annually portion. Anyways, you can go through Montgomery. Okay, या फिर मैं जब स्टडी किया था उस टाइम पे एक विली का बुक आता था, अभी याद नहीं है, बाद में अगर याद आएगा मैं तुमको बोल दूंगा. ठीक है, एक बार पिंग करके रखता, मुझे व्हाट्सएप में मिल जाएगा मेरा नंबर, उसमें तुम एक बार पिंग कर देना. ग्रुप पे पिंग कर सकते हो, ग्रुप पे पिंग कर देना, मैं तुमको उसमें एक बार भेज दूंगा. मतलब बुक का PDF होगा, आई विल फॉरवर्ड इट. ओके, बट बेसिकली तुम लोग इसको गूगल में सर्च करो तो भी ये सब टॉपिक्स मिल जाएगा. जो टॉपिक मैं बोल रहा हूँ उसको थोड़ा ध्यान से सुन लो क्या क्या है चीजें, क्योंकि 2 नंबर के क्वेश्चन आने वाले हैं. ठीक है, 4.75 मार्क्स का तो क्वेश्चन है नहीं, छोटा ही क्वेश्चन होगा, उतना बड़ा तो नहीं होगा. और आई होप कि इस पार्ट से डिस्क्रिप्टिव क्वेश्चन ज्यादा आए rather than न्यूमेरिकल्स. ठीक है, तो कुछ न्यूमेरिकल्स हैं, देयर आर सम न्यूमेरिकल प्रॉब्लम्स वी कैन हैव. मैंने कुछ न्यूमेरिकल्स आइडेंटिफाई करके रखा है, मैं इस क्लास में दे दूंगा. कुछ न्यूमेरिकल्स प्रॉब्लम्स करते करते जाऊंगा धीरे धीरे करके. अदरवाइज थियोरेटिकल चीजें याद रखना चाहिए कि कौन सा टेस्ट कब यूज होता है, रैंडम प्रोसेस का मतलब क्या है, स्टेशनरिटी कब है, नॉन स्टेशनरिटी कब है, मूविंग एवरेज क्या है, सब जो भी जितने टॉपिक्स है. ओके, so we are talking about the purely random process where we are talking about some properties which have constant mean, constant variance. Gamma k equals to 0 for all k equals to plus minus 1 plus minus 2 all for all k. Okay, so it is called as the noise, or we can say white noise. It is called as the white noise. Okay, So if it has a white noise property, and we can also call this as Gaussian white noise. White noise मैंने थोड़ी देर पहले ही बोल रहा था GWN. So it is our purely random pulse के साथ white noise का थोड़ा difference है. थोड़ा difference क्या है कि that in random process the random variables u t belongs to t, that are the sequence of random variables. Okay, but in Gaussian white noise process, these random variables are IID normal distribution, normal with 0 and sigma u square for all t. Okay, so this is the difference. So white noise and Gaussian white noise में difference यही है. In white noise we do not mention the name of the distribution. In Gaussian white noise we are mentioning that follows a normal distribution. So basically we denote it as mu t that follows GWN, Gaussian white noise, 0 sigma u square. Just remember this. So we are going to this in the next, जब भी हम लोग इसको आगे लेके जाएंगे चीजों को, इसके बारे में डिस्कस करना है. ठीक है. So you have to remember what is Gaussian white noise. Okay. So next one is the stationary process. Let's start with stationarity. Okay. So there is a suppose we can have a time series that is called the strongly or strictly stationary if the joint distribution of yt minus 1, yt minus 2, yt minus n is as same as the joint distribution of y t plus t1 plus k, y t2 plus k, in this way y tn plus k for all n t1, t2, tn and k. Okay. So joint strictly stationary तभी होगा अगर joint distribution same होगा. Okay. So obviously if we have a joint PDF, okay, joint PDF कैसे लिखते हैं हम लोग? We denote it as f of yt1 to ytn. Okay. So the condition for strong stationarity using joint PDF will be, that is the PDF is same, y t1 plus k up to y tn plus k. Okay, so for n equals to 1, suppose n equals to 1, that in that case the distribution of yt is the same for all t. So mu t equals to mu and sigma t equals to sigma square t is equal to sigma square for all t. Okay. When we have n equals to 2, suppose we are writing t1 equals to t, t2 equals to t plus k. Okay. In that case, the joint distribution depends on yt and yt plus k. इन दोनों के ऊपर डिपेंड करेगा जॉइंट डिस्ट्रीब्यूशन, क्योंकि इस टाइम वी हैव अ कोवेरिएंस और कोरिलेशन जो भी है. Okay, so in that case our, let me write it, lag t depend on lag k, sorry, lag k. Okay, so similarly we can have rho k, that is the ACF, that is gamma k by gamma naught. That will be our autocorrelation function. Okay. Next one is our mean stationarity. That is also very important topic. Mean stationary, in mean stationary, what we have, expectation of yt that is equals to mu for all t, and So to check the variance stationary, we can have expectation of yt minus mu t whole square, that is equals to sigma y square for all t. Okay, we can also have the covariance stationary. To have the covariance stationary, we can write it like that. A process is called covariance stationary if covariance in between yt and yt plus k, that is equals to gamma k for all t and k. Then it is called as the covariance stationary. Okay, so this is all about our फास्ट ऑर्डर स्टेशनरी. ओके, वी कैन ऑल्सो हैव अ और वी कैन जो हम लोगों ने डिस्कस किया स्ट्रॉन्गली स्टेशनरी को हम लोग बोलते हैं कि फास्ट ऑर्डर स्टेशनरी, एंड वी कैन ऑल्सो हैव अ वीक स्टेशनरी दैट इज कॉल्ड द सेकंड ऑर्डर स्टेशनरी. सो लेट मी राइट इट. वीक stationarity, or we can write it as a second order stationarity. So a time series that is called as weak stationarity if the mean and the variance are constant and ACVF that only depends on the lag. So ACVF. So let me write it. Mean and variance are constant and ACVF depends only on the lag. Okay, so strictly stationary implies weak stationarity, but the reverse, the converse is not always true. Okay, so converse is not true, that you should remember. Okay, so now when we have a joint distribution of the data yt1, yt2, ytn, so the stations, so the weak stationarity implies the stationarity, and when the ACF of the random process can be written as rho k equals to 1 if k equals to 0 and that is k not equal to 0. If this happens, then we can say that our weak stationarity implies strong stationarity. So converse is not true, but there is an exception. The exception is that when we have a purely random process, so I have discussed earlier कि purely random process का ACF कैसा दिखता है. Rho k that is equals to 1 if k equals to 0, and so a purely random process is a strong stationary and weak stationary. Both satisfies. Okay, so a purely random process is strong stationary as well as a weak stationary. Okay, so just let me give you some example. So suppose we have a process yt where t equals to 1, 2, and we write it as yt equals to sum over mu j, where j equals to 1 to t. So here ut t equals to 1 to, it is a purely random process. Okay, we consider this. Okay, it is a purely random process with 0 and sigma u square. Okay, हम लोग normal नहीं बोल रहे. Okay, we are not mentioning that it is normal. We are just denoting as purely random process. So in that case, अगर तुम लोग इसका mean calculate करोगे, expectation of yt that will be 0, variance of yt that will be sigma square yt, that will be t into sigma u square. Okay, and gamma t comma t plus k, that is t sigma u square. So the ACF rho t and t plus k, that will be root t by root over of t plus k. So here this process is mean stationary. Okay, mean stationary follow हो रहा है, हम लोगों ने पहले ही बोला था, but it is not a second order stationary. Okay, so it is a mean stationary but not second order stationary. Okay, that thing, जब हम लोगों को ऐसा एग्जांपल अगर एग्जाम में देता है कि स्टेशनरी चेक करने के लिए कोई ऐसा रैंडम प्रोसेस दे दिया है, तो हम लोगों को क्या करना है, मीन निकलना है, वेरियंस निकलना है, कोरिलेशन फंक्शन, ऑटो कोरिलेशन फंक्शन निकलना है, कभी पीएसईएफ भी निकलना पड़ सकता है. ठीक है, सो कैसे कैलकुलेट करते हैं ये चीज एक बार तुम लोग देख लेना बस. ठीक है, नेक्स्ट वन इज, एक और एग्जांपल लेते हैं. मैं इसीलिए एग्जांपल ले लेके दिखा रहा हूँ. You guys just go through the examples and try to solve this. Okay, ये जो examples है इसी को ही try करके देखो. What is the PSEF? What is the ACF? Okay. So if we have a process like yt equals to a cos omega t plus phi. Okay, where phi is uniform 0 comma pi. Suppose that is given. Okay, so if you try to find expectation of yt, that will be minus, if you try to find it, it will come minus 2a sin omega t, and this is a function of t. This is a function of t. So the process is not mean stationary. This process is not mean stationary. So not mean stationary. Okay, so also if you calculate like second order stationarity, okay, you guys go through it. Okay, you guys मतलब ये homework जैसा ही है, सोच लीजिए that is our homework कि you guys check whether it is a second order stationary. Okay, one more thing you have to remember, if a random variable has a mean 0, the process becomes mean stationary because it is not a function of t. Okay, fine. मैंने 2-3 एग्जांपल ले लिया, एक और एग्जांपल करवा देते हैं. So suppose we have a x that follows Poisson distribution with mu. Okay, and we have a sequence ut t equals to 1 2. That is the sequence, and the sequence has mean equals to 0, and we have sigma u square. Okay, matlab not equal to 0, sigma u square. So in that case, expectation of yt, that will come as mu, and sigma yt, sigma square yt, that will come as mu, because Poisson distribution is there, so both are same, and gamma t, that will come as mu gamma kt for all t comma k. So the process is second order stationary. Okay, and it is also called the strictly stationary. ये भी हुआ क्योंकि मीन वेरिएंस सेम है, उसके साथ कोवेरिएंस फंक्शन भी सेम हो जाएगा जॉइंट डिस्ट्रीब्यूशन के साथ. ठीक है, so that is why you can call it. So just let me give an example. ये तुम लोग घर पे ट्राई करना. Suppose we have a linear trend yi equals to, not yi, yt equals to alpha plus beta t plus mu t, where ut is normal, no, not normal, wn. Okay, white noise, 0 sigma u square. So check mean stationarity and second one is the variance stationarity. Check both. Okay, reckoning. Another example, we can write it like, suppose we have a process yt that is equals to sum over suppose aj into cos of omega jt plus phi t, phi j. Okay, and we have aj that follows normal 0 sigma square. We have this. Okay, aj follows normal 0 sigma square. So the process is mean stationarity. हम लोग ये तो देख ही रहा है, mean stationary है. Okay, right. What about the variance stationary? Check it. Okay, and suppose if phi j that follows uniform 0 pi, in that case, what will be the change? Whether it is mean stationary or variance stationary. Mean stationary देखना तो बहुत easy है. Mean 0 आ रहा है तो आ ही तो रहा है mean 0. Sum करोगे तो 0 ही आएगा yt का value. But check the variance stationarity in that case. Okay, fine. So next topic we can talk about. Let me see. अच्छा, syllabus में ये भी है ergodic process. So next we can discuss ergodic process. So suppose we have a process yt, t belongs to t, is set to strictly ergodic property, okay, with respect to a bounded function f that is bounded if for the realization of yt where t equals to 1 to, in that case अगर ये हमारे पास observations है yt, then the sample average sum over f of yt from t equals to 1 to n, आगे 1 by n होगा क्योंकि sample average है, that sample average converges almost everywhere as n tends to infinity. If that satisfies, okay, so then we call it as a ergodic process. Okay, so why it matters, why we are discussing about ergodic process? So let me just go through the example. Suppose we have a process yt where t equals to 1 to, and yt is a linear trend mu plus x plus mu t, where mu t follows GWN 0, 1. Okay, we have considered 1. Okay. And we have like the expectation of yt that will be mu, variance of yt that will be 2. Okay, and for every k the ACF that will be half. Okay, and also k that, okay, so the process is stationary and also achieves the statistical equilibrium, right? But the process revolves around mu minus 1 to mu plus 1 depending upon the initial value. Okay, so in that case this state is not unique. Okay, so what we are going to do, we are going to consider stationarity. That stationarity ensures the statistical equilibrium but not its uniqueness, right? So हम लोग इसमें इसी वजह से हम लोग लेके आ रहे हैं कि ergodic process मतलब ergodicity जो होता है, that means we have the stationary, we have also the uniqueness property. So ergodicity along with stationarity ensures that the equilibrium is unique. Okay, that means Suppose we have a single long-term series that becomes the representative of the whole data generation process. Okay, that means the samples also be the representative of the population. अगर रिप्रेजेंटेटिव ना होता मतलब अगर ओनली स्टेशनरी होता आर्गोटिक नहीं होता तो रिप्रेजेंटेटिव नहीं होता. So basically if we have a argodic property satisfied in our data set, so we can basically take a sample of the data. If you have seen that when we have a time series data, we consider the whole time series data and you do the model. Okay, why we do that? Because we know that the stationary property holds, but maybe that it is non-uniqueness. Okay, so basically this property forget the past in long terms. Okay, जिसको हम लोग बाद में जो तुम लोग किए हो शायद लॉन्ग शॉर्ट टर्म मेमोरी बोल के उसमें हम लोग यूज करते हैं. ठीक है, सो you should remember that this process, algorithmic process, forget the past in long term. Okay, okay. So हम लोग डेफिनेशन तो देख ही लिया क्या है कि कन्वर्ज कर रहे हैं इसको कौन से क्या कन्वर्ज करे कि 1/n sum over f of yt I equals t equals to 1 to n. That converges almost everywhere. So when we have a stationary process, so basically if we have a stationary process, then expectation of f of yt is always mu. So basically stationary process, in stationary process this thing converges to mu, right? So ये याद रखना चाहिए कि स्टेशनरी प्रोसेस में कहां पे कन्वर्ज हो रहा है, म्यू पे कन्वर्ज हो रहा है. ओके, सो obviously our time series has to be stationary in order to be algorithmic. Okay, ये तुम लोग याद रखना. Okay, next one is suppose we are having a data generating process. So a data generating process is mean algorithmic if limit n tends to infinity, expectation of 1/n summation yt minus mu whole square t equals to 1 to n, that is equals to 0. So the variance term, right, is 0. So we can also say that the DGP is variance algorithm. Variance algorithm if limit n tends to infinity, expectation of 1/n sum over yt minus mu whole square minus sigma square, that is equals to 0. So if that happens, we say that it is the variance algorithm. Okay, and we can also say covariance algorithm. उसका भी प्रॉपर्टी हम लोग लिख सकते हैं कि covariance algorithm में क्या होगा कि जो ये जो टर्म है अंदर में एक्सपेक्टेशन के अंदर जो टर्म है, that will be the covariance in between yt and yt plus k. हम इसको अवॉइड करते हैं. Sure. Okay, so in a process which is algorithmic in mean and autocovariance is called algorithmic in wide sense. Algorithmic in wide sense. So when the process is called algorithmic in wide sense, when the process or the you can say the algorithmic process in mean and autocovariance. So if it is limit is 0, ये जो उसका ऑटोकोवेरियंस का जो लिमिट है अगर ये भी 0 होता है एंड मीन भी 0 होता है, मीन का जो लिमिटिंग फॉर्म है, then we can say it is a wide sense. Okay, so इसका बहुत सारा एग्जाम्पल हम लोग देख सकते हैं. उसमें से एक एग्जाम्पल पकड़ते हैं. So suppose we have x follows Poisson mu, and we have zt t equals to 1 to this follows some distribution with theta minus mu and sigma square. Theta minus mu क्या adjust करने के लिए हम लोगों ने कर दिया, ठीक है, तो theta आ जाएगा. And we have a process that yt equals to x plus zt. So we have a process where x is the trend and z is the random term. Okay. So here this process not mean ergodic. If you see whether the process is mean ergodic, so it is not. It is an example. So let me write it. It's not mean ergodic. Okay. So basically क्या होगा इसमें, since we have an initial value of x का initial value लिया है, that's why the mean of the samples will revolve around x plus minus x1 minus mu. So that is why that will not be the mean ergodic. Okay. So look, ergodicity is not just a characteristics of the process. Okay. The manner in which the experiment is conducted to collect the observed time series, that is also affected by the ergodicity of the time series. Okay, that is you have to remember. Okay, so next one is the deterministic time series or deterministic process. Deterministic process. Okay. So suppose we have a covariant stationary process. Okay, and that is called a linearly deterministic if probability of yt given yt minus 1, yt minus 2, that is equals to yt. So that means our मतलब क्या हो कि yt, इसमें yt क्या हो रहा है, yt can be predicted correctly using the entire past. Okay, so if we take the one step ahead prediction, that in that case the error will be 0. Error is 0 because why it is happening, because we are correctly predicting the value of the one step prediction. Yt ka value that is completely dependent on the previous ones. Correctly predict हो रहा है, ठीक है, but it doesn't mean कि yt is non-random. Yt may be random. Okay, so to do that we can denote a shift operator that is called backward shift operator. So it is defined as b of yt, that is yt minus 1, and similarly bk yt yt minus k. Okay. Okay, sorry. So if all deterministic components of a time series have been subtracted in advance, करते हैं ना कभी कभी हम लोग बाकी निकाल लेते हैं बाहर. If we do that, we then call it as a purely non-deterministic process. So for an example, if we consider yt equals to a of cos t plus b of sin t, where a and b are independent distributed standard normal variables, जो भी है वही. So in that case, yt plus yt minus 2, if you calculate that, you will get sin 2 by sin 1 into yt minus 1. Try करके देखना, यही आएगा. So probability of yt given yt minus 1 and all others, that will become sin 2 by sin 1 into yt minus 1 minus yt minus 2, that is yt. So that example has a deterministic process. Okay. So एक और एग्जांपल हम लोग लिख सकते हैं. We can consider another example. A process yt equals to sum over aj cos of wt plus phi j, where j equals to 1 to k, and phi j that follows uniform 0 pi. So if you go through this, isko try karna, you will get that we same thing, yt plus yt minus 2, that will be like cos 2 cos omega आएगा, 2 cos omega into yt minus 1, and that thing will be deterministic. Okay, ये भी deterministic आएगा. Let me give you another example. एक और example try कर लेना. That is, suppose we have another example, yt equals to a plus bt. That is a linear model, and where n follows normal 0 1 and b also follows normal 0 1. So in that case, yt that will be 2 into yt minus 1 minus yt minus 2. That will come, and probability of this will be yt. So it is also a deterministic process. Okay, so that is all about deterministic time series process. So next one is called जनरल लिनियर प्रोसेस. तो सॉरी, उसमें जाने से पहले एक और चीज हम लोगों को देखना चाहिए, ओल्ड डिकम्पोजिशन. ओल्ड, that is also very important for exam. Okay, so what is old decomposition? Suppose we have a non-zero, so not non-zero, zero mean. We have a zero mean, let me write it, zero mean, covariance, stationary, non-deterministic process. Okay. So I have already discussed all of the terminologies. Zero mean, covariance, stationarity. First one. Okay. Also non-deterministic process. Okay. So if we have a zero mean, covariance, stationarity, non-deterministic process, okay, that can be decomposed as yt, that is equals to theta I u t minus I plus ut, where I equals to 1 to infinity. इसका मतलब क्या, मतलब है कि तुम ले रहे हो ऐसा ऐसा डिकम्पोज कर रहे हो यूजिंग थीटा 1 ut plus theta 2 ut minus 1 in this way up to infinity, मतलब जितना तक डेटा है हमारे पास. ओके, एंड उसके बाद प्लस ut. ओके, ये जो टर्म है इसके बाद. Okay, so here theta naught is 1. Okay, and sum over theta I, sorry, from theta naught से start करेंगे इसको. हाँ, from, so theta naught 1 है ना, मुझे लग रहा था 0 है. हाँ, 0 ले लिया था. So theta naught should be 1, and sum of the absolute values of all theta I square, that is less than infinity, form I equals to 0 to infinity. Okay, so that he also we can also have ut is a purely random process with zero mean and constant variance. तो बोलने वाला नहीं है हम लोग, क्योंकि पता ही है. Next one is that ut is a purely deterministic process. Okay, एक हो गया कि purely random process, एक हो गया purely deterministic process. Okay, and ut should be unique. ut का value unique होना चाहिए. So these things you have to keep in mind when you are considering it. Okay. Okay. So एक और चीज हम लोग डिस्कस करते हैं, if we have a zero mean undeterministic covariance stationary process, okay, that will be purely non-deterministic if ut is equals to 0. मतलब कोई प्योर टर्म जब भी आता है टाइम सीरीज डिकम्पोजिशन में, स्टेशनरी इस सब डिटरमिनिस्टिक प्रोसेस में, यू मीन इट शुड बी 0. If mean is 0, then we can purely normal, हम लोग noise, purely noise, जब भी term use कर रहे, we should remember that mean term should be 0. Okay. So there are some aspects of using the old decomposition. So first of all, that it allows us the dynamic evolution of the YT, okay, in the linear model. First thing. Second thing, that it depends on infinite number of parameters. Okay, क्योंकि हम लोगों के पास जितना भी पिछले पेज में लिखा था ये राइट, जितना भी हम लोग θ1 θ2 अप टू इनफाइनाइट. ओके, सो एक और चीज हो सकती है कि द पैरामीटर्स डीके वेरी अर्ली. ओके, डीके मतलब पता है ना, डीके क्या होता है कि जो डीके रेट जो पड़ा है डीप लर्निंग में लोग यूज करते हैं, वही चीज है. ओके, नेक्स्ट वन इज that old representation can be expressed as the ratio of two finite lakh values. Okay, so for example, we can write is a phi b that is called theta b by phi of b. Both are two different finite log polynomials. This is finite log, sorry, lakh polynomials 1, finite lakh polynomial 2. ओके, बट हम लोग उतना जानना नहीं है, बस मैंने मेंशन कर दिया कि याद रहने के लिए. दैट इज नॉट इन आवर सिलेबस. ओके, नेक्स्ट थिंग दैट इज वेरी इंपॉर्टेंट, जो हम लोग स्टार्ट करने वाले थे, विदाउट वर्ड रिप्रेजेंटेशन ये पॉसिबल नहीं है. दैट इज कॉल्ड द जनरल लीनियर प्रोसेस. बहुत सारा टर्म मैं एक साथ ही बोल रहा हूँ, ठीक है, अलग अलग चीजें हैं, लेकिन एक जगह पे करना है क्योंकि सिलेबस में वही है, तो एक के साथ कनेक्टेड है. All those are connected because we are considering a stationary process where the different types of stationary process we are discussing. Okay, so general linear process में क्या होता है कि suppose we have a process like this, yt equals to mu plus mu t plus summation theta I mu t minus I, where I equals to 1 to infinity. Here we are considering y equals to I equals to 1 to infinity. Okay, so look here, ut, that ut is a purely random process with mean 0 and variance sigma u square. Okay, and if you calculate the expectation of yt, that will be mu, the constant mu. Okay, so if you write mu equals to 0, and suppose let me write it here, if you write mu equals to 0, then we can express the general linear process as yt equals to 1 plus summation theta I b to the power I, जो पहले बोला उसमें I equals to 1 to infinity ut. So where the function, or you can write is like, it can be expressed as our phi b. Okay, ऐसे हम लोग भी लिख सकते इसको. So basically it is called the transfer function. So लॉन्ग शॉर्ट टर्म मेमोरी में ये ट्रांसफर फंक्शन का एक कुछ कंपोनेंट लेके डेवलप किया था. जब लॉन्ग शॉर्ट टर्म मेमोरी डेवलप किया था रिसर्च में, तो इसी को अप्लाई किया था, मतलब उसका लिटरेचर में ये पार्ट है. बिकॉज वी आर having a transfer function. And what does the transfer function मतलब कैसे काम कर रहा है transfer function basically is multiplied with our ut and gives the result of yt. So basically we are converting our general linear process into a multiplication of a transfer function and the purely random process ut. That is what we have to discuss. Okay, ये भी discuss करना है. Next one is the linear filter. Linear filter क्या है कि देखो जो let me just right, okay fine. जो ये जो function transfer function है ये क्या कर रहा है? That actually models the interrelationship between the input ut and the output yt, right? So the filter is an operator that maps the ut time series with the time series yt. So we can have a linear filter. So हम लोग एक linear filter use कर सकते हैं. So linear filter क्या कैसे काम करेगा? That will filter the white noise process. And why it is the linear? Because we are having the linear combinations of all BIs. That is why it is a linear filter. Okay, where we can have theta i's are called the filter coefficient. Filter coefficient. Okay. So this is how we can have the linear filter in our model. Okay. Okay, fine. Next thing is that the autocovariation function. So the autocovariance generating function of the general linear process is denoted as gamma b, that is equals to gamma k bk e to the power k, where k equals to minus infinity. Okay, so that is our ACBF, autocovariance function of general linear process. That is, we need to remember. Okay, so just let me give you some task. So what you are going to do, you are going to obtain the autocovariance function of the following process using the autocorrelation generating function sigma u squared equals to 1. So number one is yt equals to mu plus 0.4 u. Let me write it as ut plus let not complex it. Okay. Keep it simple. ut plus 0.4 u t minus 1. Here only we have only two ut's. Okay, ut and ut minus 1. If we consider suppose yt equals to ut plus 0.3 u t minus 1 plus 0.3 square ut minus 2, then what will happen? Just you can try this thing. Okay. So just you have to calculate the autocovariance function and you will get whether what is the filter function. Okay, fine. So next thing we are going to discuss, that is MA, moving average process. So how moving average came in the scenario, we are not going to discuss that. We all know what is how we can calculate moving average. We know that. But what about moving average process? Moving average कैसे कैलकुलेट करते हैं हम लोगों को पता है, ठीक है, उसमें हम नहीं जा रहे. अगर एग्जाम में आ भी जाता है कैलकुलेट कर लेना मूविंग एवरेज सबका. Okay, fine. So we have a process yt, t belongs to t, is called a moving average process of order Q if yt is equals to mu plus mu t plus theta 1 mu, not mu, let me write it as ut, because mu is the mean term, and ut theta 1 u t minus 1 plus theta 2 u t minus 2, in this way up to theta q u t minus q. Here we are not considering the infinite terms. Okay, we are completing after q terms. So that is why we are considering the moving average of order q. Okay, so here what are ut? Ut are the coefficients, and theta, here theta not equals to 0, sorry 1, theta not equals to 1, इसीलिए ut आ रहा है, उसके आगे कोई theta not नहीं है. Okay, and theta i's can be positive or negative based on the, मतलब जो भी है प्रोसेस के ऊपर डिपेंड कर रहा है. ठीक है. So what are the parameters? Parameters are theta 1, theta 2, theta q, mu, and sigma u square. These are the parameters, right? So what MAQ process represent? It represents yt against the current and previous errors. Okay, error मतलब ut. Okay, and a constant mu, मतलब लॉन्ग टर्म मीन. म्यू को हम लोग क्या बोलते हैं? लॉन्ग टर्म मीन. एज शुरू में मैंने बोला था कि डिकम्पोज सब कर रहे थे, राइट? सो इट इज आवर लॉन्ग टर्म मीन. Okay, so this process can be written as yt minus mu, that is equals to sum over theta j u t minus j, that is j equals to 0 to q, and also we know theta not equals to 1. So it is the moving average of white noise ut. Okay, so basically there are some properties like that key that this process do not have any memory. Okay, ये past values of y के बारे में कोई पता नहीं है. First thing. Second thing, it does have memory of random noise component of where it was. Only the random noise that is the corresponding to the past values. तो जब भी हम लोग डिस्कस करेंगे कोई टाइम सीरीज डेटा के बारे में, फॉर एग्जांपल वी आर टॉकिंग अबाउट द स्टॉक मार्केट डेटा. सो फॉर एग्जांपल टुडे अ पर्टिकुलर स्टॉक हैज अ प्राइस ऑफ 100 rupees, whether we should invest or not. Okay, so in that case we are if we are considering the moving average process, then we will consider only the error terms of the previous days, not the data. मतलब y के बारे में हम लोग बात नहीं करेंगे, ut के बारे में बस बात करेंगे. Okay, so in a moving average Q process में क्या होता है कि उसमें जो expectation of yt है that is mu, variance of yt that is expectation of yt minus mu whole square, right? So that will be sigma u square summation theta j square j equals to 0 to q, or theta not equals to 1, we know that. Okay, ये हम लोग put करेंगे. So now if we consider a moving average with q equals to 1 process for q equals to 1, in that case yt becomes mu plus ut plus theta 1 u t minus 1, right? So the variance in that case sigma y square equals to gamma naught equals to sigma u square 1 plus theta 1 square. Okay, so basically if we calculate the ACVF, you will get gamma 1 equals to theta 1 sigma u square, gamma 2 equals to 0, and gamma k equals to 0. All other are 0. Can only have the gamma 1. Okay, so if you have this, and we also know that gamma minus k equals to gamma k. मैंने पहले भी बोल रहा था ये इस के बारे में, right? So using this, the ACF of MA1 moving average 1 can be written as rho k, that is equals to gamma k by gamma naught, that is equals to theta 1 by 1 plus theta 1 square if k equals to 1, and it will be 0 if k greater than 1. Okay, देखो, when k greater than 1, in that case gamma is a 0. So gamma rho k, that will be also 0. Okay, so if you have a MA2, what will happen? So we write MA2, that means Q equals to 2. So in that case, YT will be mu plus UT plus theta 1 UT minus 1 plus theta 2 UT minus 2. So in that case, the variance will be gamma naught, that will be sigma u square 1 plus theta 1 square plus theta 2 square. So basically, gamma 1 will be theta 1 into 1 plus theta 2 sigma u square. Okay. And we have also have gamma 2. Okay. Because we have MA2. That is why there is a covariance. So theta 2 sigma u square. That will be our gamma 2. And from gamma 3 to gamma k, that will be 0. Okay. So here in autocorrelation function, we have some components. So rho k, that will be theta 1, 1 plus theta 2 by 1 plus theta 1 square plus theta 2 square for k equals to 1, and theta 2 by 1 plus theta 1 square plus theta 2 square for k equals to 2, and 0 for k greater than equals to 3. Okay, so that will be the our autocorrelation function of, this is very important. Basically, this is very important. Okay, बहुत मतलब जगह पे जहाँ पे भी क्वेश्चंस होता है ये टाइम सीरीज के ऊपर, उसमें मूविंग एवरेज से क्वेश्चन आता है, मूविंग एवरेज प्रोसेस से, उसमें MA1 MA2 इसके बारे में हर जगह पे पूछता है. Okay. And so if we have MAQ process, मतलब generalized version of this, then basically YT is equals to क्या होता, mu plus summation theta j u t minus j, j equals to 0 to q, right? q तक होता है क्योंकि infinite तक नहीं जाता ना, q तक है में q. So in that case, sigma y square, that is gamma naught, that is 1 plus theta 1 square plus theta 2 square up to theta q square sigma u square. Okay, that means sigma u square sum over theta j square, j equals to 0 to q, and theta naught equals to 1. Okay, so in that case, gamma k will be like theta k plus theta 1 theta k plus 1 plus theta q minus k into theta q into sigma u square if k equals to 1 to q, and 0 if k is greater than q, and gamma minus k if k is less than 0. So basically, if you remember the formula for the moving average process with q, then you can easily derive the formula of 1 and 2. ठीक है, जगह पे 1 बिठाओगे तो आ जाएगा ना इसका वैल्यू, right? So this is how we calculate ACVF. ये तो गामा के निकालना हम लोगों ने, इसके बाद हम लोग क्या करेंगे, रो के निकालेंगे, ACF ऑटो कोरिलेशन फंक्शन. So that is denoted as rho k, that is gamma k by gamma naught, right? So that will be like थीटा के प्लस थीटा वन क्या था मैं भूल गया, हाँ याद आया, थीटा के प्लस वन इन दिस वे, थीटा q minus k into theta k divided by 1 plus theta 1 square, theta 2 square up to theta q square. So this is the correlation coefficient if k equals to 1 to q, and it will 0 if k is greater than equals to q plus 1. So basically the autocorrelation function will vanish for k greater than equals to q plus 1. Okay. So next one is the ACF using auto covariance generating function. Because we have discussed about the autocovariance generating function, so we are going to consider the ACF. So in MA1 process में क्या होता है कि YT equals to denote as phi of B UT. So where phi of V, that is 1 plus theta 1B, because we are considering MA1 process. So you can easily calculate gamma naught sigma U square 1 plus theta 1 square from here, and gamma 1, that is sigma U square theta 1. So gamma K equals to 0. So that is, you can also calculate. Okay. So ये process है, but we are happy to consider these parts. Okay, मतलब कैसे हम लोग ये formula use करके, this is the formula, ये जो formula था इसको use करके कैसे हम कर रहे हैं, that is enough. Okay, fine. Okay, so suppose let me give an example, that is your homework. Suppose we have YT that is equals to 10 plus UT plus 0.6 UT minus 1 plus 0.3 UT minus 2. So in that case, calculate the row 1 कितना होगा, row 2 कितना होगा, and row 3 कितना होगा. Okay, row 3 to row k कितना होगा. Okay, so and also मतलब गामा आपका वैल्यू कितना होगा, ये सब निकलने का ट्राई करना, क्योंकि हो सकता है कि एग्जाम में आ जाए कि इसका वैल्यू दे दिया, ठीक है, थीटा 1 का थीटा 2 का वैल्यू दे दिया, देन व्हाट विल यू डू. Next thing we are going to discuss is called, let me check the syllabus once more. Okay, so let us discuss random walk. I hope कि stochastic में भी तुम लोगों ने random walk पढ़ा है. So basically we have a process UT, T belongs to T. It is a purely random process with mean 0 and variance sigma U square. Okay, then a random walk process YT, T belongs to T, is defined as, it is our random walk, defined as YT equals to mu plus Y T minus 1 plus UT. So the model changes. Okay, so if we have Y naught equals to 0, then by using some substitution हम लोग क्या कर सकते हैं कि YT का वैल्यू क्या आएगा, YT वैल्यू आएगा T mu, इसको हम तुम रिकर्सिव प्रोसेस में करोगे तो ये रिजल्ट आएगा YT equals to T mu प्लस समेशन ऑफ UT, इधर तुम्हारा T equals to जितना भी सम है T equals to 1 to T. ठीक है, so basically it appears that the process has linear trend. Okay, also have stochastic trend. Why? Because expectation of YT, that is equals to T mu, and variance of yt, that is equals to sigma u square into t. But here mean and variance of yt depends on t. Okay, so this process is non-stationary. So it is non-stationary. So random walk is not a stationary process. बहुत जगह पे क्वेश्चन पूछते हैं whether random walk is stationary or not. So random walk is not a stationary process because expectation of yt equals to mu t and variance of yt. That so basically here we are having a mean and variance of random walk process where mean and variance both dependent on the t time. Okay, since it is dependent, so it is not a stationary process. Okay, so there are different time series that behave like a random walk, like for example GDP random walk जैसे काम करता है, और exchange rates जितना भी exchange rates है ये सब काम करता है random walk जैसे. Okay, next we should discuss. Look, we have done moving average process, so we have also another process, important process, that is called the AR process or autoregressive process. So moving average and autoregressive are two most higher topics in time series data. Okay, जहां पर भी तुम लोग मॉडलिंग करते हो इन प्रोजेक्ट इन समथिंग, तो हम लोग मूविंग एवरेज ऑटोरेग्रेसिव यूज करते ही है. फर्स्ट ऑफ ऑल वी डू दैट, देन आफ्टर दैट कि देखते हैं कि रिजल्ट कैसा है, उसके बाद डिफरेंट एरिमा सेरिमा सेरिमैक्स जितना भी है डीप लर्निंग ये सब यूज करते हैं. बट द बेसिक थिंग्स आर दिस आर द बेसिक थिंग्स कि मूविंग एवरेज प्रोसेस क्या है, ऑटोरेग्रेसिव प्रोसेस क्या है. सो बेसिकली हम लोग थोड़ा थ्योरेटिकल पढ़ेंगे क्योंकि नेट में ऐसा ही क्वेश्चन आएगा शायद. ओके, सो an autoregressive process of order p is defined as, okay, let me just write it. And autoregressive process of order p, so right, is defined as yt that is equals to phi 1 yt minus 1 plus phi 2 yt minus 2 in this way plus phi p yt minus p plus del plus ut. So here ut is the purely random process with 0 sigma m square. Okay, here phi 1, phi 2, phi p are the parameters of the autoregressive process. Okay, next one is if expectation of yt that is equals to expectation of yt minus 1 up to expectation of yt minus p that is equals to mu, then mu equals to क्या है कि एक्सपेक्टेशन ऑफ, सपोज मान लो मैं ऐसे लिखता हूँ इसको, mu equals to del by 1 minus phi 1 minus phi 2 minus phi p. ओके, कहां से लेके आए, मॉडल से. ये मॉडल्स हम लोग ऐसे एक्सप्रेस कर सकते हैं इसको म्यू को. ओके, सो म्यू इज द जनरल इफेक्ट, जो मेन इफेक्ट जो था बेसिकली. ओके, सो वी आर कंसीडरिंग autoregressive 1, AR1. So in AR1 the parameter p has equals to 1. So yt equals to phi 1 yt minus 1 plus del plus ut. That is the model. That is the model of AR1. Okay, so here we can say that for given yt minus 1, okay, yt becomes independent of y t minus 2, y t minus 3, and all. So it is basically called as a Markovian property, right? Markovian property में भी यही होता है. So this process is called Markov process, where the mean of the Markov process mu equals to del by 1 minus phi 1, जो हम लोगों ने पिछले पेज में लिखा था, न्यू का वैल्यू, इफेक्ट का वैल्यू, that is mu equals to del by 1 minus phi 1 is for AR1 process. Okay, so if we consider del equals to 0, that means that implies mu equals to 0. So it is mean stationary. Okay, again, if we assume the process is variance stationarity, that means gamma naught equals to variance of yt equals to variance of yt minus 1 equals to all the variances equals to sigma y square for all t. So that implies sigma y square equals to, that will be the phi 1 square sigma y square plus sigma x square. तो इसको अगर हम लेके जाएंगे इस तरफ, sigma y square, that will be sigma x square by 1 minus pi 1 square. Okay, so basically if we calculate, it is our sigma u square, it is sigma u square, right? Okay, sigma u square, and in this way that will become gamma naught. ये gamma naught होगा हमारा. Okay, and in this way if we calculate the ACVF and the ACF, gamma 1 will be equals to phi 1 gamma naught, that is phi 1 sigma u square by 1 minus phi 1 square. And if you calculate like gamma k, that will be phi 1 k sigma u square by 1 minus phi 1 square. So if we consider it in year 1 process, in that case rho k will be gamma k by gamma naught, that will be phi 1 k. Okay, so if phi 1 is less than 1, that means rho k, matlab the autocorrelation declines. Okay, geometrically decline hoga. So that is the interpretation you have to remember. Okay, so if we consider an example, suppose we have a process yt equals to 0.2 yt minus 1 plus ut. In that case, ACF is like 0.2 to the power k. So if you plot it, so basically first of all, it will look like this, 1, because k equals to 0. Then k equals to 1, 0.2, k equals to 2, 0.04. In this way, it becomes 0. Okay, so it declines geometrically. Fine. Next one is, suppose we are considering AR2 with del is equals to 0. So we have the model yt equals to phi 1 yt minus 1 plus phi 2 yt minus 2 plus ut. So here we have gamma naught expectation of yt square, that will become phi 1 gamma 1 plus phi 2 gamma 2 plus sigma u square. So phi 1 become gamma 1 becomes phi 1 gamma naught plus phi 2 gamma 1, and phi 2 becomes gamma 2 becomes phi 1 gamma 1 plus phi 2 gamma naught. कुछ नहीं, बस इससे आ जा रहा है, ठीक है. So basically if you calculate phi 1 equals to phi 1 by 1 minus phi 2 gamma naught, and gamma 2 equals to phi 1 square by 1 minus phi 2 plus phi 2, इसको अगर हम लोग ऐसे डिनोट करेंगे इनटू एक और टर्म आएगा, कौन सा टर्म आएगा, गामा नॉट आएगा, इनटू गामा नॉट. सो इन दैट केस बेसिकली क्या हो रहा है कि this in a process the correlation vanishes after a certain point. It is obvious. Okay. But in air process it declines. But it never vanishes. Okay. So moving average में vanish हो जाता है. AR में जब भी हमने AR इसमें P किया है ना, ART में कभी vanish नहीं होता है. Okay. So here we have a very important equation, Ewald-Walker equations. Okay. So it is basically related to the autoregressive model parameters to the autocovariance. Okay. So we have suppose we have a ARP process that is yt equals to phi 1 y t minus 1 plus phi 2 y t minus 2, in this way phi p y t minus p plus ut. Okay, so basically this Ewald-Walker equation will provide a straightforward method for the estimation of the parameters theta is, theta 1, theta 2, theta p, इसको करने के लिए, ठीक है. So basically how it is calculated, it is basically if we calculate the expected value of yt minus k, if we calculate this, we will get that is phi 1 expectation of y t minus 1 y t minus k plus phi 2 expectation of y t minus 2 y t minus k plus कितना तक जाएगा, phi p तक जाएगा, phi p expectation of y t minus p y t minus, because we are considering ARP, that is why. If we consider AR1 then एक तक ही जाता, प्लस एक लास्ट टर्म होगा एक्सपेक्टेशन ऑफ ut y t minus k. Okay, so if you substitute with 1 0 1 up to p, and then you will get some equations. Okay, अगर तुम उसको substitute करोगे, you will get how many equations you will get? You will get p plus 1 equations. Okay, p plus 1 equations वो कैसा दिखेगा? That will be rho naught equals to phi 1 rho 1 plus phi 2 rho 2 plus phi p rho p, just phi p rho p. Okay, and we have a error terms, right? So that will be sigma u square by rho naught, not rho naught, gamma naught होगा, नीचे तो variance रहेगा gamma naught. Okay, this is the first equation. Second equation, rho 1 will be phi 1 rho naught plus phi 2 rho 1, in this way, that will be there. Okay, so basically in this way we will get rho p, last equation, phi 1 rho pu minus 1 plus phi 2 rho p minus 2, in this way phi p rho naught, and there is another equation phi naught equals to 1. Okay, so these simultaneous equations is called the Ewald-Walker equations, or you can write it in a matrix form where phi equals to p of p inverse row of P. Okay, so this is called the Euler equation. So basically, this is the matrix in the matrix form. Next one is that we can also calculate the PSCF, partial autocorrelation function, PSCF, for the air process. So if we want to eliminate the effect of all the other time points, ये सब करेंगे, then we will get a matrix one, not minus one, row one up to row k minus one, row one in this way, row k minus one. So this matrix is multiplied with AK1, AK2 to AK. A is denoted before, हम लोग बोला था row 1 to row k. So if we solve this matrix, we will get the value of AKI, and these are the autocorrelation, sorry, partial autocorrelation, autocovariance, partial autocovariance. Okay. So, for example, if you calculate an AR process, AR1 process, AR1 process. So in that case, YT is equals to phi 1 YT minus 1 plus UT, and ACF is rho k equals to phi 1 to the power k. We know that, right? लोग ने ये देख लिया. And PSCF, that will be A11 equals to rho 1. इसका मतलब इक्वेशंस जो मैट्रिक्स होगा वो कैसा होगा, 1 rho 1 rho 1 1 multiplied with A21 A22, because k is equal to 2 here, and that is rho 1 rho 2. So from here we calculated that A11 is rho 1. Okay. Next is the AR1 process. So if you want to look at the Markovian property in AR1 process, that means we are provided the value of YT minus 2, YT minus 3, ये जो जितना वैल्यू है, so these are become negligible, मतलब इसका कोई importance है नहीं, they are going to delete it from the data set, right? So basically in AR1 we are only considering YT minus 1 and YT, and this YT minus and YT becomes independent of the other YTs, YT minus 2, YT minus 3, all the previous जो जितना भी values है उसके ऊपर independent हो जाएगा. That is the first thing we consider AR autoregressive process with Markovian property, right? Next one is if AKK equals to 0. If AK equals to 0, then यदि अगर ऐसा होता है, then for k equals greater than equals to 2, it support the Markovian property. मतलब जो AR1 के लिए तो support हो ही रहा है, लेकिन AR2, AR3 इसके लिए support तभी होगा if all AKK are 0. मतलब A23, A24 up to A2P, these are अगर 0 होगा, then in that case AR2 में भी Markovian property satisfy करेगा, because covariance exist नहीं करेगा. Basically there will be no covariance in between these things, YT minus 2, YT minus 3 के साथ, YT minus 1 and YT के साथ. Okay. So one more thing, just let me tell you, because इसके बाद हम लोग next topic में जाएंगे, because अभी तो 10 बज गए हैं almost. So just remember this, कि the PSCF for AR2 process vanishes for all k greater than equals to 3. For all k greater than equals to 3, PSCF for AR2 vanishes. Okay. So basically, For ARP process, okay, PSEF vanishes when K greater than P. Greater than P basically. Greater than P. Not greater than equals to K greater than P. So that is important thing we have to. So अभी ऑटो रिग्रेसिव प्रोसेस खत्म कर लिया. इसके बाद हम लोग चलेंगे नेक्स्ट. इन द नेक्स्ट क्लास वी विल स्टार्ट विथ मिक्स्ड ARMA process. So this is the sequence. First we know moving average, then what is autoregressive, then moving average के साथ autoregressive ऐड करके क्या होगा, ठीक है. ऐसे धीरे धीरे हम लोग प्रोसेस करेंगे. ठीक है, आज के लिए इतना ही. Tomorrow we will discuss mixed ARMA process. Okay. Okay, let's sleep.